Good evening or good morning, depending on where you are. Today we have a tough problem to solve, and the problem is this one. Let me copy the matrix. The matrix is -1. Let me write it here. -1, 1, 0, 2, and the other matrix is 1, 1, 0, and -2. So what's the thing with these matrices? These matrices are in fact topologically conjugate. So that means that there exists a function, let's say h, that is an homeomorphism from R2 to R2 such that h applied on the flux of, let's say this is the matrix A and this is the matrix B. The flux applied on this matrix is equal to the flux of B of this thing. So the homomorphism gets inside and appears here. And now this is in fact not a difficult problem. We can prove this relatively quickly, but the thing that is hard is to construct the homeomorphism. What I mean is that we have a theorem. There's a theorem that tells you that two matrices, let's write it, two matrices with the same index of stability are topologically conjugate. So that means that there exists this function and so on. So it is not difficult this is when two matrices, two hyperbolic matrices. This is important. So if they are hyperbolic, then the same index of stability, and the index of stability is the number. This thing is the number of eigenvalues with negative real part. So if two matrices have the same number of non-negative real eigenvalues, non-negative real part of eigenvalues, and those matrices are hyperbolic, then those matrices are topologically conjugate. So this is a very powerful theorem. But this theorem is an existent theorem. This is a theorem about that tells you that there exists this homeomorphism, but doesn't tells you what is the homeomorphism. To find that homeomorphism, we need to construct it, and we will do it from scratch. So this is the thing that is actually difficult to do, but we will do it here, and we will do it with a couple of tricks to make it faster and more easy to prove. And this the method that I will provide you here can also be used for matrices that are bigger than 2x2 matrices. It could be used in general. It's a general procedure to construct these homomorphisms. So let's get into it. The first part will of course prove the existence of this homomorphism. So let's analyze first the matrix A. Let's work on that. So it's -1, 1, 0, and 2. So for this matrix we need to find the characteristic polynomial, and it is not difficult. This is the determinant of this thing, which is this product. And so the first eigenvalue is -1, and the second eigenvalue is 2. So given that both eigenvalues are different from 0, or well, have a real part that is different from 0, then the matrix A is hyperbolic. And it has one eigenvalue with a real negative part, so the stability index of A is equal to 1. For the second matrix, let me write it is, well, the thing. I think this is, yeah. So the characteristic polynomial will be, of course, this determinant that is equal to 1 minus lambda times minus 2 minus. So the first eigenvalue will be, let me add a page here. Yeah, the first eigenvalue will be lambda first will be 1, and the second eigenvalue will be minus 2. So both have a real part that is different from 0, then V is also hyperbolic. And it has one eigenvalue with a negative real part, so the stability index of this matrix is 1. So by means of that theorem that we mentioned previously, these two matrices are topologically conjugate. So we have proof that there exists this homeomorphism, but we don't know what it is. So we need to work on that construction. To do it, we need to calculate a few things. First, we will calculate, well, you know that the Jacobian of A, given that it has a minus 1 and R2, is equal to minus 1 and 2. Now we need to calculate pi minus 1 and p on those two matrices, such that A is equal to this thing, right? So to calculate the first one, we do it first analyzing the first eigenvalue, and we find its eigenspace, I mean its null space. So we want the kernel of minus 1, minus 1, 0, 0, and 2, minus 1. So the kernel of this matrix, and here minus 1 plus 1 is equal to 0, so this is 0, and this is 3. So every vector in this kernel satisfies that, well, if the vector v is equal to x and y, then we only have that 3 times y is equal to 0. So y is equal to 0, and this kernel is the generated subspace by this vector. So this is our eigenvector that is associated with the eigenvalue minus 1. Now for the second eigenvalue, that is 2, we calculate its null space. So any vector here, this is minus 3, will be minus 3 times x equal to 0. This is of course 0, and so this implies that x is 0, right? So this was kind of obvious. And now for the second wait, there's a I forgot to write yeah, there was a mistake, I think. I forgot to write 1 here. So it was here the y is equal to 0, and it's the same, but here there's a change. It would be -1 plus y equal to 0, and so y is equal to 3 times x, so this is 1, 3. Now we are good. This is the second eigenvector associated with the second eigenvalue. This one, so p minus 1 is, we put it as columns. And so we can do it by Gauss-Jordan, which is my favorite method, and I leave that to you. Here I already have calculated these things, so this is 0, a third, 1, and minus a third. So we stop here. This is the thing that we will use. I think this is it. We won't calculate the flux. That wasn't what we wanted to do, but let's stop here. And now let's do the same procedure for the second matrix, for the matrix B. For B, we had -1 and 2, so let's copy it here. So for the first eigenvalue, the matrix was 1, 0, 1, minus 2, 1, 0, 1, minus 2. So the kernel of 1 minus minus 1 and 2 minus minus 1 is equal to the kernel of this is 2, 0, 1, and this is -1. So wait, there's no, it's okay. No, the it was a 1, positive, not positive 1, so it is like this, and this was a -2, so because this should be 0, and this is -3. Now any vector here will hold that x minus 3y is equal to 0, so x is equal to 3y. Then this is the generated by 3, 1. And for the second eigenvalue, which was -2, the kernel of 1, -2, 0, 1, -2 would be 3, and this will be 0. So we have that 3 times, let's say any vector here holds that 3 times x is 0 and x is 0. So this is the generated by 0, 1. So this is the second vector, and this is the first. So the matrix P, the inverse of P, will be this is a column, which is 3, 1, and then 0, 1. Once again, Gauss-Jordan to find P, and I have calculated this here, and it's a third minus a third, 0, 1. Let me put it as Q, because we already have a P above. So now it appears that now we will need to calculate the fluxes, but we are not quite doing that. We will do the following. We know that by a theorem, or well, by some theory, that the matrix A is always linearly conjugate with its Jacobian form. Moreover, well, the same holds for the matrix B. And now you know that being linearly conjugated implies that they are topologically conjugated, because let's write it here. So they are also topologically conjugate. And now if we find some way to conjugate these topologically, given that the topologically conjugacy is an equivalence relation, we will prove that A and V are topologically conjugate. But moreover, it can also be proved that if we compose, let's say this is conjugated by a matrix H1, this by a function homomorphism H2, and this by a homomorphism H3, then H3 composed with H2 composed with H1 will be the homomorphism that conjugates A and V. So we can compose those homomorphisms. Now, we know which homomorphism is here because, well, you know that A is equal to this, and so when you do this, there's a theorem that tells you this. If we multiply by P both sides, we have this thing. And if we write it here, now this is what happens if we call P as our H, because you know that every matrix has an linear transformation. It has associated a linear transformation, or defines. It's a one-by-one relation. It's a bijection, I mean. So, well, it's not a bijection, I think. It's one and one. So this matrix defines a function, and you know that linear functions, and this matrix is invertible, so this is a linear function that is invertible. Linear functions are continuous, so its inverse is also continuous because it is another linear function or linear transformation. So this the function that is defined by this matrix is an homeomorphism. So if P defines an homeomorphism, then we can call that a lowercase p. Then we are saying that lowercase p applied on this function is equal to the flux of lower p applied on x. This is the structure that we have here. And so this lowercase p will be our homeomorphism. And now we know which one this is. This is p that is here. So let's copy this here. this matrix define our function from R2 into R2. So let's put it there for a moment. And now for the other one, instead of working with Q, we will, and you can check that, we will see that the homomorphism is the inverse of Q. So let's write it like this. Let me highlight it. All right. So now we have our homeomorphisms. This defines Q and homeomorphism from here. And now the only thing that is left to do is to find some homeomorphism that goes from here to here. I mean, of course, H2 goes from R2 into R2. But that works in this way. I mean, we need to find some H such that so now we need to find these fluxes now, but we had calculated these matrices, and they are both diagonal, so it's not hard to do. Let's write it. Let me copy them here. So the fluxes are kind of obvious. And the other one is this one. All right. So we need to find some homomorphism that works like this. Somehow we need to compose these things. So you can see that here we have as an exponent a minus t, and down here we have t. So first inside would be to make some inverse of this term and the inverse of x1, but that doesn't help at all because homomorphisms are meant to be bijections from R2 to R2, so they need to be defined on the whole plane. So if you divide something, then you cannot apply that on the whole plane. You will need to have the first coordinate as different from 0. And same here, if you make the inverse of the second coordinate, then it won't work because inverses are not defined on the whole plane. But what you can do is actually to make you have a minus t here, so you can square the thing and you will have a minus 2t, which is here. And in the other case, you have 2 times t, you can take the root of that and you will have t. So this is what we will do. But the thing that you need to be mindful of is that this need to be a bijection. So square roots are not bijections from R to R, not even from R to R, because it's only defined on the positives. So a first idea will be to make the square root of some absolute value, but absolute values are not bijections because it's like this, right? So it doesn't work. The solution that I designed, it's here. Let me copy it here. It's a function that is a piecewise function, and for this piecewise function we need to check that it is continuous, that there is a bijection, and that its inverse is continuous. So this will imply that it's an homeomorphism, and besides this we need to check that it actually holds this thing. So let me put it here. Let's say H go from R2 into R2. And it's defined like this in 4 cases. We will work on 4 cases. The first case is the obvious, but this whenever x is positive and y is also, non-negative and non-negative. And the second case, we keep that first coordinate, and then we do this. And here x should be negative and y is still positive. For the second case, we take a negative of y squared, and we write here. So here x is, and for the last case will be a combination of this, so minus y squared and minus x. So this whenever x is negative and y is also negative. So you can check, I leave that to you, that this function is continuous, that it's also a bijection, and the nice thing is that its inverse is also H, so which is kind of interesting. And this happens when an operation is its own inverse. For one variable, you have that the function minus 1 is equal to minus as a function. It's its own inverse. Let's write it with an m. So m of a is minus a, which is a. So this function is its own inverse, and that happens here because we have the square root and the square, so they are inverses. And one time you sweep the places, and then from the second time you sweep the places again, and so the operations are reversed. So you can check that. And it is also true that for this function, H applied on, let me copy this. Well, I can remember that. x1 and minus t. Oh, wait. Yeah. x1 minus t and x2 square of t. So if x1 is, let's just to fix ideas, let's suppose that they are both non-negative, so the exponential is always positive. So we will be in this case, so this will be equal to x2 the square of Wait a moment. And now we apply this function on this is the flux. So we are in the first case here. It will be the square of this thing, this, and this is the power of 2 of x1 and minus 2, which is equal to the flux of B on h1, x1 and x2, because you have here this term that is the same as this, right? So this is clear. For the other cases, it's more or less like the same. It's not that difficult to prove. And let's work a second case just to make sure that everything is alright. What happens when x is like this? So we apply that here. X1 is negative, so we are on this second case here. So it will be the root of the second one, and then the negative of the other one. So this, right? And since we are in this case, h of is equal to, I think it's very simple to see that this is also the flux of t on this, and the same for all of the other two cases. So this function defined like this, this function is the homeomorphism that we wanted. This is the thing. So now to sum up, we have this h1, which was p, a lowercase p. h3 was the inverse of lowercase q, and now our h2 with just h, right? So when we compose the inverse with h with p, it will be an homeomorphism from of course R2 to R2, such that, let's call that hat h of the flux of A is equal to the flux of B, and this will be the topological conjugation that we wanted to prove, to construct, I mean. So yeah, it was a lot of work. It was really kind of complicated to do. If we didn't consider this trick, it would have been more difficult, because we will need to compute these fluxes. So this, I can, if you want, I can write it down here, the fluxes, just for you to see that that it would have been more complicated. I have them computed here. So this is and the other one is this, and the other flux is this one. Just for so you understand a little of all of the work that we saved. So yeah, finding an homomorphism between that holds the property that holds this property from this flux into this flux is not really easy. It's kind of messy. So it is more, in fact, a lot more simple if we work on this, because then we compose them with q minus q and p, and those matrices you already have them, because to compute this flux you needed to find these two matrices, and also for v. So they were matrices that you already had, so there's no extra work. It just saves you a lot of time, and then you just need to compute this composition of function, which is not difficult. Of course, the other step that you also need to do is this one, and to find explicitly to find a function that defines this thing. But even then, you don't really need to do that, because this is a no, yeah, you need to do that. So yeah, you need to compute those functions, because otherwise you will need to compute the matrix that is associated with this, and yeah, there is no such a matrix. So yeah, you will need, the only extra work that you need to do is to compute these functions, but you know how to do it from your linear algebra course, so it's fine, I think. So this is it for today's video. As I told you in the introduction, proving that those matrices are topologically conjugate is easy. It's kind of a few lines to do. Yes, you just need to prove that it's hyperbolic and that it has the same stability index, and they will be topologically conjugate. But what is difficult, and it's a lot of work, is to construct the homomorphism explicitly. So yeah, this will be for today. If you have any questions, or if you found that I made some small mistakes in the calculations, you can write it down in the comments, and I will make some time to read them. And if you're interested in another topic, you can also write in the comments, and I will be happy to work on that. And if you found this video interesting, and if you found the method interesting also, and time saving, I think it's very time saving, you can like the video and subscribe for me to post more videos and stuff. So yeah, see you later.